Yeah. So, where was it? I'm not to make a mistake. So, there was one thing here I wanted to So, here on this slide, here it is. So actually, I made a mistake here, which was very politely pointed out in the break that that in fact on string it's concat. It's the append is on the string buffer. Yeah. So that's a mistake. And mistake number 2 is down here. It's actually add. It's not append. It's because I've been using another library where it's called append. So, but the point remains. It could be implemented as. It isn't. It's implemented as a string buffer with a pin, and in this case, it is add, and it does change the list. So the language is still confused. So back to the question. Back to the question is how do you get elements into a collection that can't be changed? So the first thing is to sort of present you with the functional way of thinking of a list. And essentially, traditionally, and it goes back to, I believe, 1958 and Lisp at MIT, that a list has a head and then it has a tail. So you get the first element and then there's the rest. And we don't really care about the rest until we get to it. So the idea is that you have easy access to one element, and then you have a really easy access to a collection of the rest of the elements. And that's essentially all you get. It is probably the simplest list interface you can imagine. I can't imagine anything much simpler than that. But anyway. So the idea is, if you want to build up a list with many elements, you start out with an empty list. So in functional Java, the way that they name the empty list is nil, and that's also historic, has to do with Lisp, etc. But once you have an empty list, you can construct. Const doesn't actually stand for construct, but let's assume it does. It works. You construct it out. You take an element and an empty list, and now you have a list with one element. So on this list, the length is 1, and the head is the 17 I just put in. And if I ask for the tail, I get back the empty list. So how do you add another element? Take a wild guess. Exactly right, you just do it again. So, but the original list doesn't change. So you can keep doing this. And this is the idea behind the persistent data structures, that the original list never changes, yet now you have a new list that includes the old list, and you have another element. And that's how you construct a list. Notice that you construct it. It's not like you modify it. All right, let me switch to some code, because I want to show you how I want to make sure. Yeah. So let me switch over to Eclipse. So here's a way of constructing a list. If and I'm talking about the top one here. We get a collection of integers, and then we go through them, and I'm just using a simple for each loop, and then const them together to create a list, starting out with the there it is, the empty list, and then returning that. So, in case there are no integers being passed in, we're just returning the empty list, and we're good. If there are any integers being passed in, we go through them one at a time, add them to the list, and then eventually that's the list we return. So, see how we're changing the list here at every chance. Okay? There's a little catch with this one. Can anybody figure out what it is? It's backwards. Exactly. We're counting them in front so they come up in reverse order. Alright, but it was just an example. Okay. The other way, by the way, the other way of doing it is that you can take the list and say const I, but now we're back in the situation where this, like the add construct thing, are we really modifying it, or what are we doing? So I believe that this way of writing it, the top one, is the easier way to understand it, and making sure you don't fall into that trap. You all with me? Okay. So let me go back to the presentation. Here we are. So when we use a list, like how do we actually access and work with all the elements of a list? So in this case, it's our old friend, the find. It takes a list and an element, and then it says, if the way you do this is that you use the head, and then you sort of hunt on the tail, and then you just call recursively. So in this case, find element takes a list and an element, and if you find the element, it returns the element. So in this case, it returns f if the element is equal to the head of the list, and if it is, then we return that. If not, then we look in the tail of the list if we can find the element. Right? Yeah, I'm sure if it's an error, I'll get to it. Okay, go ahead.
Just a few minutes ago, you were complaining about, what was the word? Something complexity.
Yep.
Incidental complexity. And now you're talking about recursion?
Yeah. You seem confused over that somehow? All right. So yes, so what I'm actually doing is actually divide and conquer, or what one would do in a situation like this is divide and conquer. And I don't see a much simpler way of doing it. Take the first element and then deal with the rest. Right? So in this case, I don't know of an easier way of solving this problem. Using a for loop certainly wouldn't be easier, right? And in fact, this is so easy that anybody can understand what's going on here.
Recursion might not be so easy to understand for a lot of people.
All right.
For programmers, yeah.
Okay. So the only one of the big problems, I'll take this conversation. Right. One of the big problems with recursion is the word. You don't call it recursion, we're good. If I said to one of the students of the technical school, said, hey, just call a find element on the rest of the elements, what do you think they would say? Sure, no problem. Right? Yeah, I can handle that. I'm not disagreeing that there are certain complexities behind the scenes, but they're not getting in your way of solving the problem. There's not a new problem here that you have to deal with that we introduced in trying to solve the problem. In fact, we're reusing the solution we just created up here. So that's why I don't think there's a lot more incidental complexity being added to the situation.
You're creating a lot of lists then.
Yeah. and okay, there's a whole long conversation about optimizing these programs and turning tail recursion into while loops, etc., which I was hoping not to get to. but the reason being, I think it's a technical issue, and once you get into this, you'll get it. And this was more meant to sort of like scratch the surface and stuff. You look like you had something to say. Okay.
No. So if the list is empty, okay.
Yes, exactly.
Or if the element's not in the list, which is the case.
Exactly right. So there's two problems here. So the first one was the empty list, right? Because clearly you can't take the head of an empty list because it's the empty list, right? So clearly not going to work. And also, what happens if we don't find the element? Okay. The second one you should know the solution to by now, which is option. Exactly. Right? We're going to use an option for that little problem. So let me switch over to Eclipse. There it is. And there's the exact code again. How are we doing for time? Should I just, I'll give you a good solution here, because I wrote it. So this is what we need to sort of grasp with. So either the list can be null or it can be empty, in which case we're never going to find the element, so we return none. Yeah. If it's not empty, that means we have a head. Yeah. So we can call head on it, and if the head is equal to the element, we got it, right? We found it. And if not, we're just going to say, well, let's go see if we can find it in the tail. Does that account for all problems?
No.
No.
Your original find was returning the index of the element, not the element itself.
Yes, that's true. Yeah, you're right. Apart from that. There's no tail? What do you mean?
Oh, then a mystery
So if we had to solve the problem where we needed the index for whatever reason, how would we do that? Maybe.
Pass it along.
So one of the other, go ahead.
I was gonna say an accumulator, just passing along, yeah,
Yeah.
okay.
Yeah, pass along an accumulator so we can sort of say, okay, we got to this one before we found it. So there was one other piece here. So the second one we talked about today was option. The first one was the ternary operator kind of thing. Okay, so that's not particularly pretty here. Right, it may not be the most readable thing. And you can have a long philosophical discussion about what's the right thing to do, lots of parentheses, or use something like this. I don't know. Any opinions?
Nested trailers.
Yeah. What do you think? Yeah. And what do you think about that?
No,
Because it's not particularly readable,
yeah,
right?
But once you have all that, you might as well just write a while loop or for them.
Yeah. So the other discussion you sometimes get into, especially with people who've been doing functional language for a long time, is doing returns at weird places in a functionary method. Right? They generally like to have one return statement at the end. I happen to like this most of the time because it's a nice catch-all. At the end, you can sort of print it out if you have to, or you know it's always going to go down there before you leave. You can put a breakpoint on it, that sort of thing. Other people like to short circuit, like as soon as I can get out of here, I want to get out. That's your line.
I like early returns, and I like knowing that I don't need the else in that case.
Exactly.
So it's
If you
if list
return-
equal null, return. If list head equal element, return. Return.
I see what you're saying. I will agree, I actually agree with the point that if you do a return, having the else is probably not good because it obscures this.
Yeah.
Right, it's double somehow. In every other situation, I really like having the else because it makes it clear what the logic is. Very good.
Having it this way, you're very close to how you would do it in a functional language, however, because you wouldn't have a return in a functional language, because it will just evaluate an expression. So you're almost having like a ternary, but expression here. It's as the way you would have it in a, you know, if the list is null or empty, then you evaluate one value, else your value, the value of your expression is something else it's something else again. So it follows that functional paradigm.
Yeah. So in many functional languages, the last line, or the last expression is what you return. Which language is it? What do you use?
Scala, I've learned from other functional languages as well.
So Scala definitely does it. Ruby does it.
Maybe that's also-
This. But then
Steam did, I
there
think.
is only one,
Yeah.
right? So most of these languages will do that. So that's why, that's the line of thinking I come from. Other people have other lines of thinking. Have any of you heard of programming by contract? So that's another reason to have one return statement at the bottom, because you can put in your assertions right before you leave the function. You know, your mileage may vary. There are certainly reasons, I've seen definitely reasons where in the beginning you sort of say, well, if this is null, I'm out of here. And that makes the rest of the structure much easier to read. So, all right, any other comments on this particular construction? Okay, good. We will go back to looking at. So, there we are. So the other thing I said earlier was, in functional programming, we don't do a lot of loops. In fact, if functional programming does anything for you, it's getting rid of loops, if at all possible. It's the same way. So I'm sure you've all heard in like object-oriented programming is supposed to get rid of case statements. Right? Instead, we get lasagna code. In functional programming, it's not like you will ever get rid of all loops, like forever. But there's a huge set of them that can be removed, and your code would be much easier to read. So let me give you an example of that. So a lot of this is about preserving intent, and in this particular case, it's one of the easiest problems I could solve, sort of just to get the idea across. The the idea, or the problem, okay, actually, somebody read this and tell, oh, actually, that's cheating, it's the results at the bottom. But the idea here is, the intent is to add 2 to every element of the list. And the way to do this, and this is where things get functional, is to define a function. Unfortunately, in the current state of Java, doing that requires quite a bit of syntax. In fact, the second bullet does that. All right. How many people are confused by this particular definition? Yeah. Okay. So, essentially, F stands for function. So capital F means it's a class. And what it does, it creates. So we create a class that has exactly one method, which is called F, which is the function that gets called. So since there's only one, there's no state, there's no extra elements to it, that's all we can do with it. And the only thing that it can do is to do something to the parameter that we're passing in. So in this particular case, we're defining a function that takes an integer and returns an integer. Is that clear, or is that confusing? So in Java 8, we can do an anonymous function with a lambda, you know, where we don't have to put in all this type information and all the other syntax, and we could just put it in down here. Fortunately, in 7, not the case. So in order to do this, there's a function on list called map. And essentially it takes one element and maps it to another, and it goes on to the next one, and the next one. So for each element, there's a new element in the list that gets returned, and it sort of moves along. Can anyone imagine how that might be implemented behind the scenes right now? Anybody? Yeah, or
what we just.
Recursion.
yeah, exactly. So you take the head, and you use F on the head, and then you say, oh yeah, just use it on the rest, and we're done. You get it? Okay. So what I like about this is that it preserves the intent. Right? There's no for loop, there's no index plus plus, there's none of that. Essentially we're saying, take this list, map every element using this function, and return a new list. And that's all there is to it. So that's how we get rid of for loops. Nice, huh? All right, so that's a very simple example. Let me show you another one. How to remove elements. And the trick here is to sort of redefine the problem. So if you have a list, you want to remove some elements, what you do is you define a new list with all the elements except the ones you don't want. So in this particular case, we're defining a function that takes an integer and returns a boolean. So here's the function, it takes an integer, returns a boolean, and in this case, we're just saying if the integer is bigger than 5, then return yes, good, and if not, not so much. And then we use another function on this called filter, that with that function, will only leave in the elements for which this returns true.
And that has to be a Boolean for the second type to filter with it, or not?
Yes, it
Yes.
does, and that's enforced. The type system will complain if it's not boolean. Does that make sense to everybody? I see it sort of with this like, I don't know, this is like, can I really believe this? It's like, yeah, you can believe it. It does work, and I'll show this in Eclipse in a second, but I want to make sure that we get through the examples before diving into code. Does this make sense to everybody? Is there any other place in the Java API where you might have seen something that resembles this? Yes.
What did you say?
Go ahead.
Comparative.
Comparative sort.
Yes, and sort does too. In fact, there is a sort, but I'm not going to show that.
And map and filter are in the standard list.
In the functional Java.
Oh, they're in the functional Java list.
Yeah.
Okay.
Just to do, you do a list, so you could have a class list.sort and then pass in, and then have it,
Yeah.
so you could have several different kinds of sorts passed into
So, so first of all, yes, and that's the reason why, I mean, that's one of the functional ideas that's already in the Java, the standard APIs.
Right.
Yeah, exactly. And then, the comparator you can use for two things, it's for sorting, and what's the other one? There's another place where it's used. There's, is it the one, oh, there's something similar to filter,
Yeah.
but I forget what it is. There's another one, there's another place where it's used. Anyway, here's another example of something, which is, can we find the, a certain wanted element in here? Write a function that takes an integer, in this case, and returns a boolean. So there's the integer, there's the boolean, and if it's, in this case, just 5, then we return true, in other cases we return false. Okay? We call find with this function, and it will return not an integer, but an option saying we might have found it, right? So they learned the lesson, by the way, when I wrote this code originally. Yeah, I forgot about option. Right? So it happened, right? Anyway, the correct use is, so you ask if it's none, that meaning we didn't find it, and otherwise we have a sum and we can print that out. All right, does everybody get this example?
If I'm doing an honest function like that, it's pretty ugly code at the top.
Yeah, I agree. I agree. And not only that, you can call, I can call the function what I want, but the f is kind of hard coded, you can't change those. It would be nice, I mean, some of them use apply in here instead, and then a small f for the class, but that's also pretty ugly. And you really, because the type system in Java is so limited, you can't get around all the angle brackets. Like, it simply won't work. You have to in this case, you have to return a boolean. There's no two ways about it.
So, I mean, if you had a 1 in for equal to 6, you just have to duplicate all of them?
Exactly.
Yeah, if you want to say if
You
it's a
need
5 or a 6,
No,
So-
Well, I mean, like, what if, in one case you wanna pass in 1 and 5, 1 and 6, right, two different,
yeah, you have a problem there. But the only way out from that is to have something that's final outside of this, so that you can, it captures that, and then you could compare it to anything. But now you're back in the problem that,
state.
yeah, exactly, right, you now have something that depends on something that's outside. Alright, so this was pretty, go ahead.
You can make the function concrete too, right? Like just, plus whatever bigger than x, that takes one parameter, that does have state, but you can make it immutable,
Yeah.
Yes,
right? It'll take an integer to start with, and everything will be compared to that integer.
yes, but sooner or later, if it's an object, you fall into the same trap that you capture the object, but the object can be changed. You don't have that. The other thing you could do is sort of just say new, and then put all that in here. But I found out it's hard to read, and this is, for the purpose of demonstration, this seemed like the easier or better thing to do. But you could get rid of the first line up there, if that makes your life easier. I don't know. All right, I will go into Eclipse and show you a couple more things in here. So we did here. So in the case of, I have the examples here. So you'll see the same thing here, and if I run this, you'll see that this works. Okay. So no problem there. The filter one, same thing here. There is one thing that you'll notice, which is an issue. Constantly have to do this thing, and this is a clash between the typing of the used in the library and the typing used in the functional Java library, and the typing of the JUnit assert equals. Yeah, because that only takes object. So, there's one that takes object and compares it to an object. So to make sure that
Yeah.
it's an int, you have to cast it. It's again one of those examples where, well, you know, almost, right? It's so close. If we could just get rid of that int, it'd be great. But yeah, this is where we're at. So actually, did I explain that very well? So assert equals comes in a variety of different versions. One of them takes object and object, and Java isn't able to determine which one you mean, so you have to cast so that you are specific on both parameters. Because otherwise it might say, well, you could have meant the one that takes an object, except one of them's an int, so that's not gonna work. Does that make sense? Okay, good. Running that one. And then there is the contains, same problem, right? And the two, like, option is sum is true, and then you get sum, and you get out the value that we were looking for. And now for the coup de grace, it's the, so one of the tricks to all of this is that every time we return a list, so we can do chaining, the same way you would do on the Unix command line. So in this particular case, I have the same list, I have the same add2 function, I have the same bigger than 5 function here. And now I can do the whole thing in one line. I can map with add2, and I can filter with bigger than 5, and that gives a new list where 7 is the first element. So think about this, right? This is the really clever thing, that you can just keep chaining these to get exactly what you want. Let's say it's a list of emails. I want emails after last night, sorted by date, then sorted by name. Then I only want to see the ones that that I haven't looked at already. Right? So sort by the last one was, what was the last one?
Haven't
Name.
seen it yet.
Oh, not having read. Right. So the last one would be filter, and the other ones would be sort and something like that. Right? So do you see the power of this? And also, there's no for loop.
The one line is beautiful, but all the code, yeah.
Right? That's it.
The ideal is really big
I
lists.
can
That's what the collapse
I
is
can
for.
fix that. Is that better?
One of the problems, I deal with really big lists a lot, so,
Uh-huh.
very big lists, so that may not be very efficient.
How so?
Because you're chaining it, right? So you're
Yeah.
creating a new list each time, right?
Yes, you are. So, yeah, and that's a classic discussion about this whole idea of changing and is it efficient or not. So it turns out in the modern sort of persistent libraries, if you are, how should I put this? If you're not changing the actual objects, they are almost as efficient as the mutable ones. But there are definitely cases, and I'm not going to argue that persistent data structure is the end-all be-all. There are definitely situations where you will incur some overhead. Go ahead.
But there's nothing in what you're writing at this level that makes it inefficient. It could be implemented in a way, because it's functional, because it's immutable, that is more efficient.
So there's actually the reason, I think, probably not clear, but what would actually happen for a second. So what would actually happen in this particular case if we used a mutable list? Well, nothing, because we're already creating a new one every time. But if we were, so if you're in a single-threaded, like kind of batch-oriented situation, you might do better. But remember, a list is just a bunch of references to the real objects, so it's not that bad. Is that? Yeah, I'm not disagreeing, and there are definitely situations. I'm not arguing that there isn't. So object-oriented programming, I don't know if most of you know this, actually was kind of invented to do simulations. Simula 67, right? So Norwegian invention. There has to be a Norwegian in the audience tonight, so that's why I mentioned that. They deserve all the ego boosting they can get. And to do efficient simulations like that, state is important, and the simple way of doing state is to have state, and it's efficient. I was taking another class at Coursera. It was the reactive programming class, and the first thing, the second assignment was about this discrete simulation. And the first thing the teacher sort of says, well, okay, it's better if you don't do this. Like, so he kind of threw all the functional stuff on the wayside. All right, let's do it the easy way. All right, so my point with this, that you can do this sort of thing, is that this makes your life a lot easier, it makes your programs a lot more readable, and you don't have to deal with breaks and continues inside for loops and that sort of thing to do this.
So are the lists here, are they immutable?
Yeah.
So really, I guess, and the map and filter, are they lazy or?
Since we're in Java,
Well,
they're eager.
Okay, so it's not creating a new list that gets evaluated when you do the first gate, for instance?
No,
Because they can do
it
that.
doesn't. When you call this, it gets evaluated. Did everybody catch all of that? So one of the tricks in functional programming is that I don't actually have to do any of it until I ask for this one. So I can just wait. I can just queue this up and leave it alone, and then when I call this, I don't even have to do the whole thing. I just need to get the first one, and then the rest can wait. So that ties in really nicely with the idea of you have a head and you have the rest, the tail, right? So okay, we'll do the head and then we'll wait on the rest.
And also, if you happen to have a really big list, then you're not really processing all of it. If, let's say you don't need all of it, because I
Yeah.
only need the first 10, then you're not really applying the functions.
Yeah, but a lot of what I've heard lately of people using, for instance, Scala for, is actually munching out these huge lists of data. And they're doing that. So if it was horribly inefficient, I'm sure that somebody would have said something. But get lag. Go ahead.
You might want to mention that when you add a new head to a list, you can do it with no copying at all, without destroying the existing list because of how the pointer structures are. So it's not that horrible as it looks like. You're not creating a full new, you're not copying all the elements of the list. You're adding a new pointer. That's all you're doing.
Okay.
So creating the list, I agree, that's, that should be big O one, almost, for the most part. But when you start doing stuff like this, the filter ones actually should be pretty much, that should not incur very much. Yeah, you're creating a new list, but you're pointing to the same element. Whereas with map, it's a little bit more complicated. Depends on what you're doing. You could be pointing back to old objects, or whatever that function returns, you may be pointing to a new object. There's some cost involved in that. So, but the modern ones, of which list is not one, but it's the easiest one and it works very well. But the modern ones in Scala, being vector, that sort of thing, are extremely efficient. Closure is another one where the vector is like super efficient. It's essentially a 32-way tree. So like the first level is 32 elements, and then it's 32 by 32 or something. So your access to that is nearly linear, and also the expansion is also nearly linear. It's just a big cost. All right, so you get all of this. Any other questions on this? Like when we get to Java 8 and you don't have to do silliness like this, like creating a new object and all the rest of it, and you can just do it on one line, right? This will make life a lot better. But you can start today and make your life better. So, yeah, there's yeah, I looked at I looked at a couple of things, and they weren't so I think they finally finalized the syntax, but let's just say I didn't quite. I mean, yeah, it's X and then arrow and that sort of thing. But the bigger problem is when does something become final? And I didn't want to get into that conversation here because I thought it was like that might be too much of a leap. But I might be back next month doing a talk on that. Who knows? If you can't find anybody else.
We need to sell more books.
All right. All right. So In conclusion, use the stuff that you can. So for instance, the ternary operator, use the expressions instead of, especially with assignment, because it's just much more readable and it's easier for you. Use option instead of null. Right? Don't return null if you can ever avoid it. I was going to say something about that, which was some people, and I've heard this from C programs, are like, yeah, but it's the same thing. And yeah, in a way it is. Either you have to test that something isn't like empty or null before you can use it. Yeah, that's true. But you are profoundly missing the point in that now you have the type system to help you. And you will never make the null pointer exception mistake ever again if you use option. Right? It's that simple. Then for collections, if you're using the immutable collections, generally you have fewer problems. You don't have to do defensive copying. You don't even have to worry about that. Right? You can just hand them out. If you're in a multi-thread environment, your life is just became so much easier, and you never have to worry about how do you put this, very complex testing. It's done, right? And then finally, not only does it save you a whole heap of problems, but it also makes your life easier. So you can use map, filter, find, sort, fold, and a whole host of other ones. And if you do this, you will live a happier, more productive life. All right. Well, thank you for your attention.
So, any final questions for Allan?
Good.
Did good, thank you again,
Didn't
Allan.
fall asleep.
But before you go,